A black hole is thought to be a region in space where the pulling force of gravity is so strong that light is not able to escape. The strong gravity occurs because matter is pressed into a tiny space. The compression can take place at the end of a star's life, so some black holes are the result of dying stars. From Einstein's theories of relativity that predicted the existence of black holes, and the coining of the term in 1967 and discovery in 1971, black holes have been one of the most sought-after phenomena because we have no explanation for them. We theorize that they're connected to wormholes and to different dimensions, but to be honest, we have no idea. The reason is they literally break the laws of physics as we know them. For example, black holes affect time. Just a clock runs a bit slower closer to the sea level than up on a space station. Clocks run really slow near black holes. You probably at first thought maybe causes the object, including the matter of the clock, to speed up close to the speed of light. But no, the immense gravity affects the clock, and that's why it disobeys the laws of physics. Now, physicists have created laws and theories that take black holes into account, but these are special and unitary, and they don't actually work in conjunction with the laws of physics. How does a black hole work? Think of it like this. A black hole is a waterfall, and a beam of light the kayak. Far away from the waterfall, the current is weak, and the kayak can get away, but the closer the kayak gets to the waterfall, the harder and harder it is to get away, until the water gets finally sucked in, and there's no escape. There are many pitches and flaws to the existence and the components of black holes. Some things are definite, but there are some theories created by people in the 1970s that weren't so thought through. For example, according to the general laws of relativity, nothing can escape black holes, so they should only get bigger over time as they swallow up objects and stars. But in the 1970s, Stephen Hawking pointed out that a quirk of mechanics, matter actually can escape. Quantum mechanics says pairs of particles constantly pop into existence and immediately self-annihilate. When a pair forms at the event horizon, one can fall into the black hole while the other drifts away, instead of disappearing. That particle effectively carries out some matter away, and eventually the black hole will evaporate entirely. But the flaw is that this small quantum mechanical effect, dubbed Hawking radiation, has big implications that physicists are just now puzzling out. Those particles are linked like magic dice that always adds up to 7. Once a surviving particle loses its partner across the event horizon, it would link itself to a new one. But according to relativity, the particle inside the event horizon doesn't know anything's changed. So it still thinks it's happily linked to the partner. There's a monogamy problem, because the surviving partner can't be linked to both a new particle and an old one. Quantum entanglement doesn't entitle any particle to have 3 partners at one time. Same with the other particle, the new one it's paired to. It also wants to have 3 particles at one time, and according to newfound research, it does. But this can't be possible. So how does it happen? Though there are some things that are uncertain about black holes, there are some things that are definite to physicists now. On the very outside of the black hole, there is the ergosphere that covers it until we actually get to the hole. On the very boundary of that, there's the static limit, where the current, from our recent analogy, actually starts to take place. Inside it, there's an axis of rotation that rotates the black hole like any other star or planet. There's the outer horizon, leading into the inner horizon, and then in the center, the singularity. I don't want to get technical, but there are a few properties that are substantial, that are necessary to be equated. For example, if we were to find the properties of a black hole, we wouldn't use a very complicated equation. We'd just use something like q squared plus j over m squared is greater or equal to m squared. This basically means while the mass of a black hole can take a positive value, the charge and angular momentum are constrained by mass. In Planck units, the total electric charge in Q, from our equation, and total angular momentum J are expected to satisfy the equation until the black hole's mass is equal or greater. Lastly, I'll leave you with this. What would happen if you went into a black hole? Well, as you accelerate towards the black hole, someone watching you will see you contort as if looking at you through a magnifying glass. What's more, due to the theory of special relativity, the closer you get to an onlooker, you appear to slow down. When you reach the event horizon, you would appear to freeze as someone hit the pause button. You would remain there, plastered, motionless to anyone, stretching there across the surface as growing heat begins to engulf you. According to onlookers, the stretching of space, the stopping of time, and the fires of Hawking radiation would obliterate you. Before you ever cross the line to the black hole's darkness, you're reduced to ash. But before we plan your funeral, let's forget about the onlooker's view of this gruesome scene and point out your view. Now something even stranger has happened. Nothing. You sail right through into nature's most ominous destination, without so much as a bump or a jiggle, and certainly no stretching, slowing, or scalding radiation. That's because you're in free fall, and therefore you feel no gravity, something Einstein called his happiest thought. After all, the event horizon is not a brick wall floating in space. It's an artifact of perspective. An observer who remains outside the black hole can't see through it, because it swallows up all the light. But that's not your problem. As far as you're concerned, there is no horizon. Sure, if the black hole were smaller, you'd have a problem. The force of gravity wouldn't be much stronger at your feet than your head, stretching out like a piece of spaghetti. But lucky for you, there's one big one, millions of a time more massive than our sun. So the forces that might spaghettify you are feeble enough to ignore you. In fact, a bigger black hole, you could live out the rest of your life pretty much normally before dying at the singularity.